everyone hear me okay? Cool. So today I'm going to talk about Hedera Hashgraph and what we're building. So I think the first thing to cover is what is Hashgraph. So Hashgraph is a consensus algorithm, just like proof-of-work blockchain is a consensus algorithm, except it has a few properties that is a significant enhancement over blockchain. So the first is Hashgraph is extremely fast. We're hitting over 100,000 transactions per second in a single shard. Compare that to single or double digits for other public ledgers out there. It is secure. It reaches the highest level of security possible in distributed consensus. This level of security called asynchronous Byzantine fault tolerance, or ABFT. And lastly, Hashgraph introduces for the first time in distributed consensus the concept of fairness, meaning that there's no member of the community that can affect or manipulate the order of the transactions that enter into the ledger. So before I dive deeper into Hashgraph, I think it's helpful to touch on the various categories of consensus mechanisms that currently exist in the marketplace. The first is what we categorize as a leader-based system. And this is commonly used, or this architecture is commonly used by the likes of Hyperledger or R3's Corda. And the way it works is quite simple. As members of the community create transactions, they send the transactions to a leader in the network. The leader orders the transactions and sends this ordered list of transactions back out to all the other members of the network. Now, throughput is relatively fast. We're talking about maybe a few hundred transactions per second. We've seen as high as, or platforms have claimed a few thousand transactions per second, but in general, they hover around the 1,000 TPS range. Now, there is one big flaw in this architecture, in that because there is a leader, there now is a single point of failure within the network. So I'll give you an example. If any one of these members gets compromised, right? You see, by definition, every member knows the IP address of the leader. So if any one of these members get compromised, they can send the IP address of the leader out to an attacker, and the attacker can launch an attack on the leader, or maybe a DDoS, a distributed denial of service attack on the leader, and that can shut down or disrupt the network. So that's a big flaw in this architecture. It is also not fair, meaning that because there's a leader and the leader is responsible for ordering the transactions in the ledger, then if the leader is compromised, the leader can manipulate the order of the transactions entering into the ledger. The next type of consensus mechanism everyone should be very familiar with is proof-of-work blockchain. Transactions are sent out to a group of miners. Miners compete to solve a cryptographic puzzle. The miner that solves the puzzle first wins the right to seal the next block onto the blockchain. Now, this is more secure than a leader-based system because you don't know which miner is going to solve the puzzle first. However, as we all know, it's extremely slow. Bitcoin at about 5 transactions per second, Ethereum at about 15 to 20 transactions per second. It is also not fair in that the miners can affect the order of the transactions that enter into the ledger. In fact, they very actively do that. The miners will put in transactions that pay them the highest transaction fees. And as everyone knows, this is also extremely energy inefficient. So the proof-of-work blockchain is used in a public ledger. All these public ledgers are evolving because they're seeing that there are so many limitations with proof-of-work that they're evolving into what we categorize as an economy-based system. And there are a couple of ways to, there's a lot of variety in these economy-based systems, but essentially they all rely on one fundamental assumption. And the assumption is one of rationality, that each member of the network will be rational to optimize the economic situation. However, that's a flawed assumption. Now, if I'm Edgar, I own a node on the network, I could be rational. I will want to maximize my economic situation. But my node could be infected by a virus. And the virus could be written such that it is, the node is spending money or losing money in order to disrupt the network, right? So that the assumption of rationality is an incorrect one. And you can also never write mathematical proofs around the security of these systems because they are inherently chaotic systems. In the same way that a stock market is an inherently chaotic system, you can never write a math proof to say that the stock market will never crash again. You can never write a math proof to say that these economy-based systems will never be shut down. The next type of consensus mechanism has existed in computer science for about 30 years. It's called a voting-based algorithm. And the way it works is quite simple. Each member of the network members of the network will send out a question, usually related to the order of the transactions, out to all the other members of the network. The members of the network will then each cast a vote. So the question could be something like, did the red transaction come before the green transaction? Every member of the network casts a vote, and they have to send that vote out to all the other members of the network. And then each member of the network, as they receive that vote, also sends out a receipt, again, out to all the other members of the network. It is extremely bandwidth inefficient because of all these transactions that needs to be sent over the network. Now that's fine if you're ordering, if you have, call it 8 members of the network and you're trying to order 2 transactions. But if you're talking about 1,000 nodes on a network, you're then talking about 1 million messages that needs to be sent over a network just to order 2 transactions. So it's not scalable. And for that reason, this has never been implemented in any way practically. However, the reason it's important is because it achieves the highest level of security possible in distributed consensus. This level of security called ABFT, or asynchronous Byzantine fault tolerance. Now, so the question is, are you able to create a mechanism that does voting, or that follows this voting-based mechanism, but without votes having to be sent over a network? And that's exactly what Lehman, Dr. Lehman Baird, our chief scientist and the inventor of Hashgraph, had created with the Hashgraph consensus mechanism. So again, I'll touch on the properties of Hashgraph. Hashgraph is extremely fast, over 100,000 transactions per second in our cryptocurrency transactions in a single shard. It is asynchronous Byzantine fault tolerant at the highest level of security possible. And Hashgraph also introduces for the first time the concept of fairness, where no member of the community can manipulate the order of transactions that enter into the ledger. So every transaction has a fair timestamp associated with it. Now, in the next slides, or next set of slides, I'm going to talk about how the Hashgraph consensus algorithm works. It's actually quite simple and quite brilliant. So these are all nodes in the network. Alice creates the red transaction. She picks another member of the network randomly, in this case Dave, and she gossips the transaction out to Dave. So Hashgraph uses the gossip protocol, which is quite common in computer science. So Alice gossips the red transaction out to Dave, and then in the next round, Alice and Dave pick another member of the network randomly, in this case Gina and Bob, and they gossip the red transaction out to them. And very quickly, in the next round, every member of the network receives the red transaction. Next, you have Bob and Carol each creating a transaction, the green and the blue transaction, at around the same time. And this transaction, again, gets gossiped out to other members of the network. And exponentially, the entire network receives all the transactions. So at this point, every member of the network has all the transactions, but what you're still missing is the network has not come to an agreement yet on the order of the transactions, right? And that's where the next step comes in. So go back. This diagram can be drawn to look like this next diagram, this diagram right here. Time goes up this way. Alice, Bob, and Carol, these are all nodes in the network. And each of these circles is what we call a gossip event. And in each of these events would be one node gossiping to another node a certain set of transactions. So this event, for example, could be Alice gossiping over to Bob, the red transaction. So in these events, there's a transaction, and very importantly, and this is really where the innovation comes in, along with the red transaction, we include two hashes. The hash of the prior event that Alice created, which is this event right here, and the hash of the prior event that Bob created, which is this event right here. So again, this event will have the hash of this event and this event. And subsequently, Bob will gossip back to Alice, and this event will have the hash of this event and this event. So these two hashes allow us to create this diagram. And this diagram is what we call the hash graph, a graph linked together by cryptographic hashes. Can we move to the next slide? So this is the hash graph. Time goes up this way. If you look at this event right here of Dave gossiping over to Alice, as she receives this gossip event, because of those hashes, she's able to recreate this entire diagram below this event, right? And she can keep it in her local copy of the database. And as Alice gossips over to Bob here, Bob can also recreate this entire image of the hash graph below this event right here. And that is, as Bob gossips over to Charlie, Charlie is able to recreate the entire image of the hash graph. So what you have is the top of the hash graph, there's a discovery process that goes on over time. As information is as the transactions are being gossiped around to nodes in the network. But at the bottom of the hash graph, every single member of the network has the same identical image of the hash graph. And the hash graph gives you the entire history of who has talked to who and when. So if you go back to the voting-based algorithm that, like I said, has existed for 30 years, instead of Alice asking Bob, hey, did the red transaction come before the green transaction? Alice, by looking at her local copy of the hash graph, is able to calculate what Bob would have voted if she were to have asked Bob that question. And she can calculate what Charlie would vote on that question and what Dave would vote on that question. So without votes being cast over the network, each member of the network is able to calculate the votes of everybody else in the network. And that is how we're able to achieve such high transaction speeds, because the bandwidth requirement is so low. So what you have is a consensus mechanism algorithm that is ABFT and extremely low bandwidth requirements. So if we go back a couple of slides. One more? Yeah. Go forward a bit. One more. Yeah. So what we're really gossiping to other nodes in the network is every transaction that the sender knows that the receiver does not know yet. So in this case, if Bob is gossiping over to Hank, and Hank already has the red and the green, so Bob is only sending the blue transaction over to Hank, right? So in distributed consensus, every node in a network needs to know what everyone else knows, right? It's a distributed ledger. And all we're adding is two hashes to each of these gossip events. right? Bytes of information. So we make the claim, and I absolutely believe this to be true, that Leemon has solved the problem of distributed consensus at scale. You cannot do better from a security standpoint, and it's extremely difficult to do better from a throughput or bandwidth requirement standpoint. Let's move forward. So Hashgraph can do everything that blockchain can do. And it also introduces a whole set of other use cases, right? Like I said, the combination of high throughput, high security, and very importantly, fairness allows you to build applications that just are not possible today on existing blockchain technologies. So up until March of 2018, Hashgraph was only used in private permission use cases with enterprises. But in March of 2018, we announced Hedera. And Hedera is the public ledger built on top of the Hashgraph consensus algorithm. And it's the only public ledger built on the Hashgraph consensus mechanism. And what we're building with Hedera is a platform, a public ledger for the mainstream. And if you look at the public ledgers today, there's very little mainstream adoption of the public ledgers. And we've narrowed it down to 4 main reasons. Performance, you just cannot do very much with 5 to 20 transactions per second. Security, if you need a platform to transact trillions of dollars on top of, you need the highest level of security possible. Stability, what we've seen with all the prominent public ledgers today is that as a public ledger gets more well-known or more valuable, there's a tendency for it to fork because incentives are there for people to fork the ledger. And that, while there certainly is a place for forking of ledgers, we believe that introduces instability and that prevents mainstream adoption, multinational corporations from wanting to build applications on these public ledgers. Now, I'll give you a quick example. If you're launching a securities token, for example, where you are tokenizing a real estate property worth $100 million, what happens is that public ledger forks. Now you have 2 sets of tokens, trying to claim the same asset. That's chaotic, and that creates instability. And lastly, you need to have good governance for a platform for the mainstream. And so everything that we've done with Hedera has been with these 4 main issues in mind. And where we're working is to solve all these limitations. So the Hashgraph consensus mechanism solves the first 2. Like I said, we're hitting over 100,000 TPS. Hashgraph is ABFT. With stability, so Hashgraph is a patented technology, but at version 1 of the network, we are going to publish the entire source code on GitHub for anyone to view. So we're not hiding anything. There's full transparency, and we believe that. We believe that you need to have full transparency in order to have a platform that people can trust. So what we're doing with the patent is really just to provide stability to the network. We're using the patent to prevent forking of the public ledger. And lastly, for governance, we are putting together a council of up to 39 of the largest corporations from around the world. These are Fortune 500 type companies, brand names that everyone here would have heard of. And we're going to be announcing the first tranche of 5 council members at our event next month, which will be February of 2019. So our ecosystem, we have a variety of Fortune 500 companies that have expressed interest and committed to governing the platform. We have over 100 dApps that have committed to building applications on our platform. We have over 40,000 downloads of our SDK, various partners within our ecosystem, and more than 5,000, I think it's over 6,000 now, developers in our Discord channel. And those numbers continue to grow over time. And this slide just shows, gives you an example of all the companies that have committed to build the application on Hedera. So that's it for my overview. I'm next going to hand it over to my colleague, Kelvin Cheng, who is our developer advocate for Asia. And Kelvin's going to talk about how developers can start to build applications on Hedera.
So this is a recorded video of Ken and the My name is Kelvin. I'm one of the developer advocates for...
Let me hand this over to you.
Okay. But maybe I don't need it for the recording purpose. Hi. My name is Kelvin. I'm one of the team members who work under Ken. This is Serene. She's also a developer advocate. So we have been working with Hedera for the past 6-7 months, getting really involved with developing the SDKs. And more recently, we have released a Chrome extension, which is almost the equivalent of Ethereum's MetaMask. Right? It is in the early stages, but you can actually go to the Chrome store, download that, and give that a spin. Try out our micropayment demo on a website called Daily Timestamp, where you pay a tiny amount of H-bars. H-bars is the name of our token to consume content on a publisher website. So that's an interesting use case, which proves that you don't have to wait for minutes in order to view an article if you use some other blockchain. So here's a quick video. We're not going to show everything. You can watch everything yourself. We're just going to jump to, if you're a developer, we're just going to jump to the section where you download the SDK and look at a very quick code example. Yeah.
You should have gotten this at a hackathon.
So to use, to register an account, you can go to portal.hedera.com to participate in our community testing program and register an account. Once you have done that, you can download, you can clone our SDK, start a Golang project, for example, if Golang is your thing, and start using it. So this is a quick demo.
And load this as a new module in Go. So we do that by doing the Go mod init, and then you have to give it a GitHub name because that's how modules work in Go. I'm just making up a GitHub organization and calling it ZTM Go. That's fine. Mod still works with it. So if you look in the directory, you can see that go.mod is the only thing there. And I'm going to add a file called keys.go so we can go ahead and create those keys. I'm going to open this up in Visual Studio Code. You can use whatever IDE you want. I generally use Golang from IntelliJ, but Visual Studio Code is just fine. So we get to start this like any other package. Obviously, you got to start with package main. We're going to do our imports. I'm going to import format and the Hedera SDK for Go. That can be found at github.com/hashgraph/Hedera SDK Go. And then, of course, func main. So now I'm creating a secret, and this is as simple as just calling the Hedera client and asking to generate a secret key for me.
We can skip forward a little bit. Yeah.
Grab it like I am. Submit button.
Yeah.
Grab it like I am right now, because I need that public key when I jump back into the portal and drop that public key into the public key spot.
Yeah.
Now
So-
click the submit button.
So if you are developing, if you want to try out a simple application on Hedera network, you can easily register with your public key and essentially get going. You will get an account ID, and that account ID will be what you'll be used to transact with the Hedera network. So it's really quite simple. Our SDKs are still in early stages. Interestingly, a lot of community members have already started coming forward to help us. We have a lot of inquiries about a JavaScript SDK. Because Serene and myself have been working exclusively on JavaScript, the extension, Chrome extension, for the past 2 months. So we are very familiar with the JavaScript. We do not have an official JavaScript SDK yet, but we will have it soon. And if you want to contribute your time to help us to move it forward faster, that would be awesome. We'll be happy to work together with you to build up our SDKs. So if you jump to our documentation very quickly, more information about how you get things done can be found here. If you have any questions, just feel free to reach out to us on Discord, right? Besides the two of us, there's 4 others, developer advocates spread across US, Europe, and Asia. So just ask us any questions, reach out to us directly, and yeah, get your application going. It's pretty cool.
So question?
Do you want to sum it?
Yeah, no, it's
Happy to answer any questions if you have. Yeah.
I'd like to ask, so if, let's say, a project or developer wants to build on Hashgraph, I see that some of the SDKs are ready and some community members have come forward to support. Is there also any other form of like official support or anything, any resources that they should be aware of that could help them?
Right now, the people providing support are mostly the developer advocates. That's us.
Alright,
So
so
that's-
two of you, yeah.
There's 6 of us in
6 of
total.
you, okay.
Right, 2 in US, 2 in Europe, and 2 in Asia. I know that Ken is hiring more, so we are growing our developer advocate team alongside with the community that's sprouting around Hedera. There's a lot of companies who want to build on us, and 6 person is not enough to support all of them. So we are growing fast.
And maybe just to touch on timelines a little bit, we are right now in the community testing phase, but we're expecting the network will be openly accessible to all developers in March or April of this year. So you can start building on the platform without even talking to us.
Yeah. So right now you have to go through the portal to register in this testing phase. But once we are open access, you can do whatever you like because it is a public ledger.
The mainnet is out, right?
This is the beta. Yeah.
So is this the testnet?
This is the testnet and the mainnet. The mainnet is live too. Both the testnet and mainnet are live, but we don't call it 1.0 yet because we are going through testing. So all the new applications that are built on us are also helping us to iron out kinks that are still in the new code base. Right? It's a brand new code base that we have built from scratch on top of the Hashgraph algorithm that Edgar has introduced. So there are a lot of little services that we have to tie up in order to call it 1.0. The 1.0 event is what we call open access, and that will happen sometime 2 to 3 months from now. As an estimate. I can't give you any guarantees.
So you said the testnet and the mainnet are live, but mainnet is not around, so
No, testnet and mainnet are live.
mainnet is running.
Yes, that's right. The community testing program is where you can register an account and you'll be rewarded with mainnet H bars, real cryptocurrency, to do the testing.
So one question on like how the ecosystem. So you have 100 DFs building on you, super exciting. Can you share with us maybe some of the kind of infrastructure components there? So for example, is there like some kind of like name service or like DEXs or some of these fundamental components? Which might be helpful?
There are a few interesting applications are trying to build a name service.
Yeah.
In fact, we will be going to Hong Kong to work with them on the 11th of February. It's one of the companies that are incubated by a Helix, right? It's called a Helix Accelerator. The VC involved is called Mindfund. They are a deep tech investor, and Helix Accelerator is a special partnership between Hedera and this VC to specifically finance companies who wants to build a business around the Hedera network.
Yeah, well, to finance and incubate companies that are building on Hedera Hashgraph.
So are there any major use cases that you guys are looking for, like areas you feel like you want to channel your energy into incubating or financing?
Yeah, I'll touch on that. Well, the truth is, you can really build any application that you want to build on. You're thinking of building, you can build on the Hedera public ledger. Having said that, we feel like the features of Hedera are uniquely suited for micropayments, and because of our high transaction throughput, we can do micropayments really better than any other public ledger out there. So if you're talking about media sites where instead of hitting paywalls or instead of being, where you are the product and your information is being sold to advertisers, we can create a new business model where every consumer can make a micropayment every time they view a web page. So that's and this can be done with web pages, can be done for music streaming, and really a variety of different applications. And we already have companies that are building these applications on the platform.